Welcome to another RDWorks Learning Lab. Today, I don't know what to call today. It's going to be a bit of a reflection day because I've been spending a lot of time thinking about this small, very high intense beam and the way it isn't performing the way you'd expect as it passes through lenses. Now, I've had lots of interesting support in the form of "you're an idiot, you're doing it wrong, you'll never succeed" type of support. That's a bit like a red rag to a bull. And for me, I'm pretty convinced that there's still some serious advantage to working with a high intensity beam at low wattage. But I'm getting some really confusing results from some of my dotty tests that I'm doing with compound lenses. And I thought that today I really ought to go back to my early design days when I remember my mentor saying to me, two things particularly always come to mind. One, understanding a problem completely is 50% of the solution. And the other thing he used to say was, exaggerate or simplify to help you understand. Now, I think that's what I'm going to have to do today. I've got no idea where we're going, but I'm going to start off by using my mechanical background to pull the mechanical elements out of optical technology, if you like. I mean, for example, we know that light travels in straight lines. I know that light has got several strange properties. It can be a photon, you know, this massless thing, blob of energy that is here all the time. We see it around us. Well, we don't see it around us, but it's here. We don't see it until it hits something. That's when these photons give up their energy, when they collide with this material. The other way that light exists is in the form of light rays. And we all know what a light ray is. It's probably, and I say probably because, as I said, I'm not a physicist either, but I suspect a light ray is a continuum of photons. That's what it looks like or feels like to me. And then, of course, there's another way that you can look at light, apart from being these little particles of energy. You can look at it in the form of waves. And when you get waves of light, you get all sorts of strange effects like diffraction and things like that. Well, I'm not so sure how much of that actually comes into our technology, but I'm not ruling it out. We're going to start off with light rays, because light rays are easy to understand, and that's how lenses are designed, using light rays. And it is the refraction of those light rays that gives us our lensing effect. Now, the aberration PDF that I've borrowed this from, I've mentioned many times before. It's a fantastic document that explains quite a lot about aberration and lenses. And here we see the aberration caused by a plano convex lens. So what I want to do now is to use that imagination and simplification that my mentor mentioned many years ago. We're going to imagine this to be a square lens, not a round lens. And it happens to be 1 centimetre square. And every one of the squares inside that 1 square centimetre will be a millimetre. So there'll be 100 rays within this square lens. Every one of those rays that I'm talking about is going to be 1 watt. Because I'm going to be firing 100 watts of energy, not necessarily laser energy. I'm just going to give these a number, 1 watt, so that you can see what we're actually going to be talking about. So 100 watts over 1 square centimetre makes that 100 watts per square centimetre. Now, these parallel light rays, which are all exactly the same power, 1 watt, they will hit the lens and they will refract twice. Once as they go into the material and once as they come out of the material, and they will be guided and refracted towards this general area here. Let's call it a focal point. And that's the function of a lens. Let me ask you this very simple question. I'm putting 1 watt into this lens and it's being refracted and bent. What's coming out? The lens doesn't do anything to the ray itself. All it does is refract it and bend it. So I've still got 100 watts worth of rays coming out of this square lens. But what's happening to those rays? Now let's just take it right to the extreme here and say that just here, let's forget about this aberration and assume that all these rays happen to coincide at this point here, which I'm going to say is 1 square millimetre. So I've got every one of these rays stacked on top of each other at this point here. So if this is only 1 millimetre square and I've compressed 100 watts into it, then I've now got 10,000 watts per square centimetre. So I want you to come along and imagine with me yet again that just at that point there we've got 1 square millimetre, and 1 square millimetre is going to finish up there as 1 square millimetre. So that 1 square millimetre there is not going to change at all. But then again, that 1 millimetre there is not going to change at all, or that one. But what is going to happen, if you look very carefully down here, you'll see that that 1 square millimetre is going to stay 1 square millimetre all on its own until it gets towards this area here. As these rays get closer together, the 1 square millimetres start overlapping here, and they start combining together to increase the power before they even get this far. As we start approaching down here, we've got a combination of these rays gradually building and building and building to get towards this 10,000. You'll notice that they're building from the outside towards the centre. They're not actually building down the centre, not until we get to the very last minute here. So look, we've got this like this arrowhead, and that's a very important point that I have observed, and I would like you to take with you when we get to the next stage of this simplification. So I will just remind you that at this point here we've got uniform energy density at the rate of 100 watts per square centimetre. When we compress it down to 1 millimetre, again we've got a uniform intensity, but it's 10,000 watts per square centimetre now. So the 1 square millimetre through the centre remained constant, whereas these 1 square millimetres on their way to the party joined up with others, and we got a gradually increasing energy density from the outside. And if you squint your eyes, you can see that in that picture. We've simplified the picture now with less rays. We've turned the lens over so that it has got really serious aberration. These rays are no longer uniform. They are going to assume an intensity proportionate to this Gaussian distribution. The ray in the centre is going to have maximum intensity. Its maximum potential to do damage to material. If you expose a piece of material to high intensity for a short period of time, it will do damage. You can expose a lower intensity to the same material for a longer period of time, and it will do the same amount of damage. So here we've got our point of highest intensity, this ray here. And this ray here, remember, is passing right through the centre and is not changed at all. It's just passing right through the middle there and carrying on to infinity with exactly the same value as what it had here. Now, the two rays that are adjacent to that are passing slightly away from centre, and they will be very, very, very slightly focused. Now, very, very slightly focused means they're going to be very, very slightly amplified, but they're already very, very high. So it's really strange that the ray that passes through the middle is not going to be amplified, but the ray that is either side of that one magic ray are going to be amplified. So we're going to have to ignore the central ray, which basically is dead, but either side of that we're going to get some amplification. This ray here, which is worth nothing anyway, its damage potential is almost nil. This one here, maybe a little bit more. This one here is starting to become a little bit dangerous. This one here is definitely going to be able to do some damage, and these here are the ones that are really going to damage our material. But several things you can note. First of all, where it's starting to damage the material is a substantially different focal point to the ray focal point. So the focal point of intensity is different to the focal point of the rays, all because we've got different intensity, different damage potential in each one of these rays. Okay, now I'm going to just step through little bits and pieces of a video that I made recently about the principle of cutting. That's the size of my beam when I leave it on for, say, 5 or 6 seconds. It will cut a 10mm hole. The manufacturer says that it's a 5mm beam. Here I've got a piece of 1 inch thick acrylic. And what you're seeing now is 1, 2, 3 seconds worth. So that's 9 seconds, and this is 10 seconds. I mean, look at all this washing machine action that's taking place inside the beam there. Now, that's something called a mode burn. The points on these are nothing to do with focus, because this is a raw beam. There is no lens involved. Now, you'll note here how this hole is the same size as the last one at 10 seconds, but look at the inside of the hole here. It's got like a countersink in the top here, which tends to disappear the longer time we allow. The more time, the more exposure time you allow, the more this low energy will get a chance to do damage. And you can see exactly that between here and here. Look, it's had a chance to damage it completely here and remove it. Right, now I'm going to do something silly. I'm going to put a 190mm focal length lens in the system. 26mm is how far that lens is inside this lens tube. This doesn't look like 190mm, does it? Well, that's because it's not. It's only from about there to there. It's about 60mm, roughly a third of the way towards the focal point. So there is definitely, again, no focal point in the beam as it hits this surface. So here's what a 1 second burn looks like. So now I've set the distance between the lens and the work to roughly 2/3 of the focal distance, about 120mm. And here's what a 1 second burn looks like 2/3 of the way to the focal point. Now that's a 1 second burn. So that's a burn with the raw beam, and it's 6mm diameter. This looks like about 4 or 5mm diameter, part way down a 190mm focal length beam. We're effectively sampling the beam part way down. This again is not a focal point. This is just a point of high intensity light. And then when we move to 120mm, roughly 2/3 of the way down the beam, look, we've got a much smaller entry, because the beam is smaller at this point because it's beginning to be focused, but it's not focus. And this point down here is not a point of focus. This is damage caused by the intensity profile at the surface. Having passed through a lens, we're sampling the intensity profile across here. And then with this very thin one, we're sampling the intensity profile here. We're still not at the focal point. This is just another type of mode burn. It's not a cut, even though it might look like a cut. There is no focus involved there. Then I set the beam to the correct focal distance. This is a 190mm focal length beam, remember. 70 watts, and this is a 1 second burn, and it burnt right through the bottom there. So I had to change the burn to a half a second, and here's what it did in half a second. So it's already going twice as fast, more than twice as fast as this 1 second burn, and now I'm at the focal point. I might be at the focal point, but the focus is not involved with the burn of this hole. So what the focus has done is brought the beam down to that diameter there to produce damage at the surface. So what we're seeing here is an exposure time and the intensity profile across the beam at that point where it enters the material. Any lower intensity beams outside here are not going to add to that hole, that damage. But what they are going to do is, if you take a look around the outside here, you'll see that there is damage on the surface. I now change the lens to a 1-inch focal length lens. And remember, a 1-inch focal length lens has supposedly got a much smaller spot size. In other words, its energy density when it hits the surface of this material is substantially higher than it is for a 7.5-inch lens. Oops, it's bigger. Okay, now that was with the lens set correctly at the focal point 25.4 on the surface. I then did a little bit of experimentation, but this time instead of 25.4 it was 24.5. In other words, I had actually pushed the focal point into the material by roughly a millimetre. So it's much wider beam than the 7.5-inch beam. That just doesn't make sense. But the other thing that we need to note here is, look just here. Look how small the entry point is just here. But then look what happens after the entry point. It starts to balloon out. So it's got a small entry point, but then there's damage happening after the entry point. And I have a full explanation for that, which we'll talk about later on. But none of this is making any sense. These are both done with the same lens combination. The top one, which is going upwards, is done on the light blade 70-watt machine. And yet, look, I've got a much smaller, finer beam on the bottom one, done on the 30-watt machine, but it doesn't penetrate as deeply. Something weird going on. I then tried to analyse what was happening with the 1-inch lens. Why was it ballooning, whereas the 7.5-inch lens was not ballooning? It was going straight down, producing a much thinner beam than this 1.5-inch lens. It just didn't make sense at all. And then I began to realise the entry hole here is very small, but because the beam has actually got very acute angles on it, like this, what's happening is some of these beams which are close to the centre line are also themselves at quite an acute angle, and they still possess lots of intensity. And they're leaking through this little teeny weeny hole here and scouring away the inside of the hole that's been produced by the central beam down here. So this is basically exposure time damage by some of these beams that are just adjacent to the centre line, but at quite an acute angle. Now, when you've got a 7.5-inch beam, those rays that are close to the centre line, like these, they're at a very shallow angle. And so consequently, the effect of those rays, although they might be bigger at the entry point here, is to force their way through and not grow. So yes, I may well have a bigger entry point here, but that also means I've got room to put more intensity into the beam, and that intensity or damage potential is actually very close to the centre line, which is why I'm able to get a very deep hole. So that started me thinking in a completely different direction. Maybe I shouldn't be using a short focus lens to try and get more power into it with a small high intensity entry point. Maybe I need more power, more intensity to get through a bigger hole. Let's try and do something stupid. Let's try and test this with 30 watts and a very high intensity narrow beam. So just to verify before we start, I tested the beam right at the centre of the machine where we've got the smallest beam. And then I popped the 7.5-inch lens in, and these are the results. The beam is quite thick and the penetration is probably twice as much as I've achieved before. As you can see, we've got A, B, C, D, E, F, G and H there. Well, A was done at a focal distance of 112. B was done at 102. C was done at 92, and then they run 82 all the way down to 42 as the last one. This is a 190mm focal length lens. It didn't work anywhere near 190mm. All it did was to just gently dimple the surface. You'll remember that the beam on this machine has been specifically set to look like this for probably around about plus or minus 200mm either side of centre. And once we get outside that zone, the beam starts growing. Here's what the beam looks like. It's bigger than that, but look what it does to the intensity profiles of these. We're nearly matching the 70-watt machine in terms of penetration, but that's because I've increased the beam from that to that. Now, it's not a lot of difference. If we take a look, you'll see the conical entry here is quite large here, and then just here it probably looks as though this is the smallest entry point here. And this depth here was achieved, this maximum depth was achieved with a focal distance of 132. So it's still 60mm short of the lens focal distance. My next strategy will be to go back and change the diameter of the beam slightly, increase it very slightly. This is still quite an intense beam, but it looks as though it needs to go a little bit bigger to get what I'm looking for. So I'm not giving up just yet.